All right, so this is a detour. How many of you have ever heard of the Variance Some Law before? Raise your hand or do the little thumbs up thing if you've seen the Variance Some Law before. Nobody. Awesome. All right. So what the Variance Some Law states is even if I just have two variables, let's say I have x variable and a y variable, and I want to create an x-y composite. If I add them together, or if I subtract them, either way, I can find the variance of this composite. All right. Does everybody know what I mean by composite, by the way? I should probably ask that question first. So, composite is like with the CESD was like what, 20 questions or something. So you took those 20 questions and you added up their scores. You scored it and added up all those items into a single score. So you took those multiple items and created a single composite that represented represented depression. So if I have an x-y variable and I want to add them up or subtract them to create a composite, I can actually estimate the variance of this composite using this down here, this variance sum law. It's a little bit trippy when you think about it, because what it's saying is the variance of either x plus y or x minus y, either way, I'm going to add up the two variances, the variance of x and the variance of y. I'm going to add them. Whether I'm adding x and y together or subtracting them, I'm going to add their variances. But what matters is if I'm adding them together, I'm going to add their 2 times their covariance. But if I'm subtracting them, I'm going to subtract 2 times their covariance. Okay? Do I have an example on here? I do, but not in a way that's going to prove to you what I'm saying. Here, let's do this. Now from your, let's look at the test. Those. I mean, we have the. This is for this one. Let's see, assignments. The one I just did was 3. Actually, this is what I want, pre-post. So here are those pre-post scores for the CESD that you can probably obviously tell it wasn't all of you, but I added your scores to a previous class's scores so that you can, you see this, right? That way you can, we can actually do this, because with just 10 scores, we wouldn't get very far. But the last 10 scores or so are from this class and the volunteers that you used. So one thing we can do is figure out what is the variance of these items, the variance of the pretest. Okay, so that's the variance of the pretest, and I can do the variance of the post-test as well. Okay, so it looks like the post-test has a little bit more variance to it. All right, so here are the variances. Now let's look at the covariance between the two of them. Actually, I think do that one. So there, oops, 2 feet arguments, because I need array 2. All right, so there's the covariance. This is how much variation they share between the two of them. So now let's look at something here. Here is pre plus post. Here is pre minus post. Okay, so if I take this plus that, and I'm creating a composite of the 2 pre and post scores. I can do that for everybody. So this is everyone's pre plus post, like that. And I can do the same thing by saying I want to take doesn't make a difference. Pre minus post, like that. And then I can calculate the variances for both of those, and they are different. All right. But we should be able to roughly estimate them by the variance sum law. So here are my two variances. The variance says that if I'm adding these two together, I should add up their variances and then add in 2 times their covariance. All right, so let's see if that works. Equals this plus this plus do 2 times that. Look at that. And if I want to subtract them, the only difference is I need to do this one plus that one. I'm going to add them still. The only difference is I'm now going to subtract 2 times the covariance because I'm subtracting the two numbers to make the composite. Look at that. Everybody follow what I just did? Ask questions. Where did I lose you? Right. So if I have a bunch of subscales for an inventory and I want to add them together, piece them together to create a composite, I can do it. I can actually add up everyone's score and do all this stuff, but I don't need to. All I really need is their variances and covariances. If I have variances and covariances, I can actually figure all that stuff out without having to look at the individual person's change or their items or their scores or the composites. All I need to know is how much variance is there in the items or in the subscales and the covariance between the subscales, and I can actually figure out what the composite measure would look like. And that's super helpful because I can start to think about reliability in a slightly different way. All right, this is sort of what we're leading towards. Like, why is it important to know the variance and covariance, and it adds up to this variance sum law? Is because we're going to use that in our favor to estimate reliability in a different way. Okay. So often multiple items are combined and create a composite, and we know it follows this rule fairly straightforward. We can actually expand this out. If I had X, Y, and Z, I can just use the variance of X, Y, and Z plus or minus 2 times the covariance of X and Y, plus 2 times the covariance of X and Z, plus 2 times the covariance of Y and Z. I can expand this out the more and more items I have. What that really does is it allows us to look at we talked about like variance and covariance matrices, like before, a little bit, I think. We can actually look at a variance covariance matrix like this. So given multiple variables, we can create a variance covariance matrix. For down the center, this is so this is X and X. All right, so this is the variance of X, because the covariance between X and itself is just the variance of X. This is the variance of X2. This is the variance of X3. And then the off diagonals, I have the covariance between X2 and X1 and 2, covariance between X1 and 3, covariance between X2 and 3. And these 3 covariances repeat down here. So even though this says 2, 1, the covariance between X2 and X1 is the same thing as it is for X1 and X2. They're just going to repeat themselves. All right, so there's the upper the part that is above the diagonal here is the same as the part that's below the diagonal there. And diagonal, I mean this part. This diagonal is actually the variances. The off diagonals here are the covariances, and they just repeat on both sides. So make sure that's clear. Ask questions here, because we're going to talk about how we can use this to our advantage. Questions about this? Variances down the diagonal, covariances on the off diagonal. All right. So here is a covariance matrix for x, y, and z. So again, given the format, we know that this is the variance of x, this is the variance of y, this is the variance of z. This is the, who wants to tell me what this one is? Yep, which is why it's the same as the covariance of y and x. Those two numbers are the same number. This one's the covariance between z and x. This is the covariance between x and z. Same number. This is the covariance between z and y. This is the covariance between y and z. Same number. Okay. So think about that for a second. Knowing we just talked about the variance sum law. If I was to add x plus y plus z, now I don't even have their numbers. I don't have the individual scores for these. I can't technically add them up, but I don't have to. If all I want to know is just the total composite variance, I can just expand it out. So that would mean the total variance, adding up x, y, and z together, would be just the variance of x plus the variance of y plus the variance of z, plus 2 times the covariance of x and y, 2 times the covariance of x and z, 2 times the covariance of y and z, which is another way of saying just add up everything in this matrix. Because I have 2 times the covariance between x and y, I have 2 times the covariance between x and z, and I have 2 times the covariance between y and z. So if I just take and add everything in this matrix together, it's going to give me the total variance. The only way that this would be different, or you have to do it a little differently, would be to, if it was y like or x minus y minus z or something like that, you'd have to add the variances up and then subtract out the covariances added up. But for the most part, we don't when we're making composites, we don't typically subtract them. We're usually adding up items or adding up subscales to create larger composites. So all we need to do is just have the covariance matrix, add up all the components in the matrix, and it'll give me the total variance for the composite if I added up those items or those subscales or whatever x, y, and z are. I can just add them up. Okay, so this adds up the variance of each item plus 1, 2 times all their covariances, and it will give me the variance of the composite. I think I get an example. Yeah, so by the variance sum law, the composite variance here would be, this is figured out. It's not a whole lot of fun, but you take, so it's 55.83 plus 29.52. Actually, let's do it in order. With some kind of semblance of an order. Let's add up the variances first. So 17.49 plus 29.06. So here, this is, so far, these are all the variances, right? Together. So now I need to add up. I can either add up 29.52 plus 29.52 and 30.33, but I can do that. I can just say, all right, I want 2 times 29.52 plus 2 times 30.33 plus 2 times 16.15. If I add all that up, what I would get is my total variance. It's probably on your slide. No, it's not. It's not on your slide. You're saying it's mine. I used to have it written out. I deleted it, so we could write it out together. What would that look like? Somebody else confirm that. Perfect. All right, now, if we wanted to think about consistency between X, Y, and Z, like are X, Y, and Z sort of consistent, are people scoring consistently across X, Y, and Z? What do we know about them right now that would help us understand how consistent they are based on what's given in this? What part of this is measuring sort of consistency? What is a measure of consistent scoring? Like being above the mean on two variables or below the mean on two variables? Yeah. So these things here tell me how consistent the pairs of variables are, right? So these are the covariances. They give me a little bit of an idea. It's not something I can really use in and of themselves. These are the covariances, and they tell me, okay, I got a weird measure, 29.52 between X and Y and 30.33. It's really hard to sort of use them individually. But what if I sum them up? If I sum 2 times all the covariances, what do I get? What's this? What's the sum of 2 times all the covariances between X, Y, and Z? If I sum all those up, what do I get? All right, so I got a 152, which is the sum of my covariances. Is 152 even? Okay, so 152 is the sum of all the covariances. Now, what would that do for me? How would that be beneficial for me to know that the sum of the covariances is 152? That's what I meant. Sum of 2 times the covariances. Yeah, that's fine. It's like all the covariances add up on this part here. So 152 is the sum of 2 times all the covariances, right? How could I use that? That would be beneficial. That would tell me something about the consistency of scoring on these 3 items. Let's take a guess. What information do we know? I know that 152 units here are the covariances. Maybe, but don't go there yet. We're going to, but you're stepping ahead of things. But what can tell me? What could I use? What could I do with this 152 that would tell me something useful about the degree of consistency between X, Y, and Z? Yeah, I mean they are all positive. That's something that once we get to where we're going with Chromebox Alpha, they have to be positive, which means even if they're negative, you have to flip items to make them positive. But we'll come back to that shortly. So 152 units of what is covariance? So I have 152 units of covariance. Doesn't matter what the scale is, but relative to what? 152 of the of the total variability of adding X, Y, and Z together. Right? 254. That was weird. I'm not like dyslexic, but every once in a while. Like I literally said 254 and my hand wrote 245. That's just weird. 254.38. I can actually get a ratio. So what percentage of the total variance is covariance? 59.75. All right, so this tells me, this is actually a pretty interesting way of thinking about it. So of the three items, if we were to add them together, we'd have a total variance of 254.38. And of that total variance, I'm getting roughly 60% of the total variability in the composite is due to covariance. With me? So the more covariance there is between items, the larger the covariance is going to get relative to the total. This number is going to get higher. The more consistent and covariant items are, the larger the proportion of covariance will be relative to the total variance. More covariance means more consistency between the scores. I don't even have to look at the scores. All I need is the variances and covariances, and I can figure out what proportion of the total composite variance is due to covariance, and it starts to give me a percentage. Like I can get a percentage of covariance. Now, this in and of itself is sort of useful, but what it doesn't do is control for a couple things, like the number of items. Obviously, more items are going to have more covariance, larger variance. So we need to think about how to control for the number of items and a couple other things. But this basic idea of what is the proportion of the total variance in the composite that is due to covariance is what led down the road to the Chromebox Alpha. Okay, so one way of thinking about this is something called internal consistency reliability, which is what gets used quite often for any sort of multi-item scale, like the CESD or any other thing where there's multiple questions measuring the same thing on a scale. We want to see if items on that scale are internally consistent, meaning are people responding in a way that seems consistent across the items? If they are, then the items are measuring the same thing. We don't necessarily know what, but they're measuring at least the same thing across multiple items. If people are not responding consistently, meaning, think about depression. If I'm someone who is very depressed, I'm going to score high on items measuring depression, across multiple items measuring depression. If I'm someone who's not depressed, I'm going to score low. And so I should be consistent across items measuring depression. If I am high or low, or even in the middle, I should score relatively consistent if they're all measuring the same construct. With me so far? All right, so one way we can start thinking about that is, all right, well, how do we start to measure the level of consistency across multiple items? And we sort of we touched on it a little bit. We can look at their covariances and think about, all right, well, how much covariance is there relative to the amount of variance in each item? And that's where we can back up. So coefficient or Chromebox alpha, depending on what you read, something's called coefficient alpha, something's called Chromebox alpha, is a widely used measure of internal consistency for continuous data. And basically, it comes down to knowing that a composite is the sum of the variances and covariances. We can basically look at consistency by how much covariance exists between the items relative to the total variance. The more covariance there is between the items relative to the total variance, the more internally consistent the items are. There. So this measure says the sum of Sij over the sum of the variance of the total. So this is the way of seeing this is the sum of all covariances. This is the composite variance. And we're now controlling for the number of items. So k is the number of items over k minus 1 number of items as a way of controlling. Because so more items, it's going to be different. If you're summing up more things, you should be able to control for the fact you have more items versus less items. So that's basically the idea. Chromebox Office says the more covariance there is relative to the total composite variance, the more reliable those items are, the more internally consistent they are. That's it. It's pretty, it's like it's a thing that gets used all the time. People report Chromebox Alpha for reliability on multiple item scales all the time, every day, all over the place, all over many psychology, social sciences. All over the place you see Chromebox Alpha used because it's a way of measuring whether or not items sort of hang together. Are they all measuring the same thing? If I'm creating a depression inventory that's say 20 items, I want to show that those 20 items are reliably consistent using something like Chromebox Alpha. Because if they're not, then it's hard for me to argue that they're all measuring the same thing. Okay, so if I want to show that items are all measuring the same construct and are reliably consistent, Chromebox alpha is a very easy, straightforward, widely acceptable way of doing that. So let's look at that in action here. The total variance is 254.41. The sum of all the covariances is 152.03. So the sum of all the covariances, 152.03. This is the total of 254.41. And there's only 3 items, so it's going to be 3 over 2. Gives me what? That's not equal 3 over 2 times that. Three divided by 254.41 equals times 3 divided by 2. I get 0.896. So it tells me those 3 items have a reliability of roughly 0.896. All right, so these 3 items are highly reliable because a large chunk of their total variability, if you add them up, is due to their sort of large covariances relative to their variances. Okay, that's it. That's Chromebox alpha. How much covariance is there relative to all the variance? And it controls for the number of items. And you get a nice reliability measure. And we look at this in the same way as we do any other. This is looked at as an R. All right, so it's reliability. That we call it an A, it's an alpha. But it's the same idea. It's the reliability, the internal consistency reliability amongst multiple items. Anytime you see a scale mentioned or talked about, like the back depression inventory, the CESD, whatever it is, they're oftentimes going to throw out there the reliability of the scale. And more often than not, it's going to be the internal consistency reliability, because I don't have to give this twice. I don't have to do it multiple times. I don't have to do anything except give it to multiple people and then look at the internal consistency of the items themselves without having to look at test, retest, or other things. This is just looking at the items themselves without having to give it multiple times or have multiple versions or split halves or all that kind of stuff. But I do have to have multiple items. If my entire questionnaire or whatever is just one item, I can't do an internal, or even 2 items. I can't really do an internal consistency measure based on that. Okay. Questions about, go ahead. So if I add up all the covariances, I'm going to add up this one, and that one, and that one, but also that one, and that one. Or I can just do it once multiplied by 2, because they're the same. So this sum of ij is literally going sum of 1 with 2, 1 with 3, 1 with 2, 1 with 3, 2 with 3, but then also 3 with 1, 3 with 2, and 2 with 1. I mean, it's doing all combinations of I and j, which means I'm doing these 3 and those 3, or I can sum these 3 up and multiply it by 2. Cool. You can also, a quicker way, especially if you have a lot of items, if you don't want to sum up all the covariances, you can simply take the total, subtract the sum of the variances. All right, so if I go back to here again, if I want to add up this, and that, and that, that's going to be the same thing as taking the total and just subtracting the the diagonal numbers, the variances. I'll give it the same number. I'll get the same 152.03 by taking the total variance and subtracting out the sum of the variances. It's just another way of thinking about it. If I take the total minus the sum of the variances, I'll get the same sum of the covariances, and I can find Cronbach's alpha that way. It's still looking at what is the total covariance relative to the total variance, which is the variance and covariances added together. It gives me a sort of proportion of covariance, and then I can sort of control for the number of items, and it gives me a nice internal consistency measure I can use to test my reliability. Okay. All right. Let's move on. Yeah. Where? Oh, I and J. So it's just a fancy way of saying. Go back a second. It's right here, where it says Sij is a covariance between the ith and jth items, where I is not equal to j. Meaning that if I'm taking the covariance of I and j, the I and j can't be the same number. So this is not going to be the S of 1, 1. Or the S of 2, 2, because those are the variances. So the I and j have to be different numbers. So the S of 1, so if you think about these, instead of being x, y, and z being 1, 2, and 3, 1, 2, and 3. So I don't want the S of 1, 1, that's going to be the variance. I want it of 2, 1, because I and j have to be different, which is this one. Or 3 and 1, which is this one. So it's just saying that I want the covariance between different variables, not the covariance between the same variable and itself, because then that's the variance. Yeah. So it shouldn't ever be like Sii or Sjj. It's always going to be Sij, some two different variables together. All right, good stuff. So I think if you were to do them, you would likely get So if I'm taking like test 1, test at time 1, the same test at time 2, okay? The correlation between the two of these tells you how much the test is reliable across time. And this is looking at the entire test. So this test is already a composite. The items have already been added up together. And so let's say you take the CESD at time 1, CESD at time 2, they're your total scores at time 1 and time 2. So it's looking at the reliability of the entire test across time. Cronbach's alpha is asking a different question. It's actually a way of sort of flipping reliability on its ear a little bit. Because now we're not talking about reliability across time, reliability across forms, which is what all the other ones do. We're talking about sort of internal reliability. Are the items reliable to each other on the same scale, which this doesn't answer? Because I've added up over them. You know, I took all the items and I just added them up to create a composite score, and then I looked at how much that composite is consistent across time. But I didn't stop to ask, well, are the items within this, right? Because this is made up of, you know, item 1, item 2, item 3, right? All the way to item, I think there's 20 or something. Item 20, right? If it's the CESD, this is made up of those same, you know, I1 through I20, right? I didn't really ask, are these items reliably consistent to each other at time 1? Because maybe they aren't. I can add up any old numbers, any old things I want, and see that they're reliable across time. It doesn't necessarily mean that they're all measuring the same thing. So it's asking different questions. It's actually, again, why sort of reliability is this complicated thing, because it really means different things. Are items on a scale reliably consistent to one another? It's a different question than saying, if I add up all those items, do I get the same total from time 1 to time 2? You know, and the scale as a whole is consistent across time. Retest reliability addresses the time-related error. You know, the error that gets introduced because of time in between testing. Internal consistency is looking at more of the sort of item-related error, that the items you chose on this scale could be introducing more or less error if they're more or less consistent with one another. So Cronbach's alpha is looking within the test test, retest, split half. Well, split half is sort of like a short form Chromebox alpha. Let's look at test, retest. It's still looking at internal consistency, but it's only looking at the halves of the test at a time. Or Chromebox alpha is looking at all the items and all the pairs together. So split half and Chromebox alpha are doing the same thing, or same idea, this sort of internal consistency. And I think if you were to take, there's some goofy thing, or if you were to take the split half of every conceivable split half you can make, cut the items up in every conceivable different halves, and average all those out, you would get Chromebox alpha. All right, because it's looking at the internal consistency of all possible combinations, which is what this is doing with by looking at the covariance. So this is looking at within the test. Test retest is looking at across time. So it's looking at different types of error that's getting sort of introduced into the scales. What you just asked, what you just said, made me like so happy. You're like thinking about this in a very cool way. It's an advanced way of thinking about things. Well, if I'm trying to create a scale that has multiple subscales, the fact that you're even thinking about it as multiple subscales, it's an excellent question, because most of these scales, and we know this, like even the CESD, other things, they have subscales. They have, there's different types of depression, different sub types of depression, and oftentimes people ignore those and just want to know overall depression, right? But there are times when it's important to know the subscales, and there's different uses for things, and the way we approach it gets complicated. Because if I have an entire scale that has multiple subscales, my internal consistency may actually be kind of low if I just look at all the items and ignore the subscales. And if I look at the subscales, it only has a few items at a time. It also may be low because they're only looking at a few items together. So you may be in this thing where you have this perfectly viable scale, but the reliability, the Chromebox alpha, isn't really working in a good way to show that it's actually reliable. So when scales start to get more complicated, Chromebox alpha stops being super useful, at least not in the short run, which is why we're going to talk about factor analysis in a little while, which is an alternative to looking at things. And you can actually look at much more complicated structures for scales, where you have both subscales and general, like overall scores for scales at the same time. And you can actually test for all kinds of crazy complex structures that Chromebox alpha can't handle. And Chromebox alpha can't handle negative covariances either, where factor analysis can, and there's things that factor analysis can do that Chromebox alpha can't. But what Chromebox alpha can do that factor analysis can't is be very simple to understand. Like people, Chromebox alpha is super easy. Look, I get a 0.8 or above, I'm good. 0.8 or below, it's not good. It's a fairly simple thing to explain. Factor analysis is a lot more complicated. So even though it's a lot more advanced in how it can handle data and what it can tell you, you oftentimes will lose a lot of your audience because it's over their head. We start talking about factor analysis a little bit. So we're going to talk about factor analysis in a very super conceptual way. We're not going to get into the mathematics at all, but I want you to understand what factor analysis is and how it's used and how it can be a good tool. Actually, it's like one of the go-to tools in developing and testing sort of scales, especially when they have multiple related subscales to each other. You can actually get into a lot more complicated ways of testing for internal consistency and things like that. Matter of fact, you're not going to see a whole lot of scales developed without at least principal components, which is the type of factor analysis, but factor analysis in general. All right. What if you're not using a test, but instead observing individuals? So there's another way of thinking about reliability too, is we have sort of observations that are oftentimes the thing we're trying to find out they're reliable. So how can we tell if judges, assessors? So you have 5 people, they're all watching kids playing on a playground. You're looking for aggressive behaviors, and everyone has to sort of write down when they see aggressive behavior on the playground. How do you sort of judge whether or not their judgments, these judges sort of anytime they sort of see something happening or don't happening, like how do you judge whether or not there actually is some consistency or reliability between those judges, which is a completely different way of thinking about reliability as well. How do we make sure that our judges, our people, are actually reliable across different behaviors or different instances, scenarios? This is actually, to me, one of the harder ones to sort of figure out, because people in general are not very good at doing things like making judgments or recording behavior. They get distracted, they drift away from the original sort of ideas. There's all kinds of issues. So looking at the reliability across people can be tough, but it can be done. So typically a set of criteria are established for judging the behavior. So you have to have some kind of rubric. Here's the kind of behaviors we're looking for. Here's how you would score them. Here's how you'd mark them down. Then to establish reliability of both the set of criteria and the judge, multiple judges need to then rate the thing. Use the rubric and then watch the video and rate behaviors or whatever they're doing. They need to actually apply the rubric. Then you look at correlations between the judges to see how well they did. If they didn't agree and their reliability is not very good, you go back to the rubric and you fix it. You change how the scoring mechanism goes. You try to make it more specific. You try to clarify things. You have them use it again, and you see if they're more reliable. If you get to a certain point where they get to a point where they are, at a 0.8 reliability, then you figure out the rubric, the instructions are sort of clear enough, and you're done, and you can sort of then start to apply it. But there's an issue here that you don't have with items on a scale, is that you could, because they're talking about behaviors, either the behavior happened or it didn't. So these are just sort of simple yes/no questions. So it's possible for judges to agree by accident. So especially if the scale, like I said, is dichotomous, yes, no, or ordinal, like the behavior was like no, non-aggressive, a little aggressive, a lot aggressive, very, like if there's some kind of ordinal scale, it's very easy for people to agree simply by accident. Like they just randomly agree. So oftentimes we will adjust for this, for the amount of random agreement when looking at the reliability of observations. So this is something called Cohen's kappa, or kappa is a measure of the inter-rater reliability. So now we have test, retest, parallel forms, split half, which is just another way of doing parallel forms. We have internal consistency, which is Cronbach's. And now we're talking about inter-rater reliability that controls for chance agreement. Values range from -1, which means there's not very much agreement at all, to 1, which is perfect agreement. And something like 0.75 is excellent. Between 0.4 and 0.75 is fair to good. Below 0.4 is very poor agreement between your raters. The way this gets done, actually, that's it. I guess that's all I really talked about here. I don't even give you an equation. I just wanted to mention that this is a thing that can be done. It takes the degree of agreement. It looks at the amount of it figures out the amount of time that people could agree by accident and adjust for it, and that's it. I'm not going to really go too much into reliability of observations. That's not really what the class is about. It's more about test theory. It's not really testing. It's more about rubrics and sort of looking at behavior. But I did want to throw it in there that there is reliability of observations, and it does fall in the same idea of reliability. It's just not in the same way as sort of test development is. This is not developing rubrics, developing scoring or rating systems, which is similar than the same thread, but a little bit outside of what we're talking about. That's why there's not even any, that's it. So one of the things we talked about error in these measures. So how do we actually figure out a way to measure that error? Well, we can, so far we talked about measurement error as the error associated with trying to estimate the true score. And the error can come from many sources. And what we can actually do is once we start to figure out the reliability, then we can actually calculate the actual reliability itself. So we get where the standard error of measurement is simply the standard deviation of the scale. So the sum total of the depression items or whatever it is, and you look at the standard deviation of that scale times the square root of 1 minus the reliability. The reason why that is because if the reliability is the amount of variability that's shared, the 1 minus reliability is the amount of variability that is not shared. So S is the standard deviation, R is the reliability. You simply multiply this out and it gives you the standard error of measurement for that scale. It tells you like roughly how much error is in the scale that you're using. So using the same continuous items X, Y, and Z, if we actually total it up to 254.41, and where S is the square root of that 254.41, meaning this is the variance of the composite, and this is the standard deviation of the composite. And we know that alpha is 0.8964. We can plug that in and say that this is 15.95 times the square root of 1 minus 0.8964. And that would tell me for the composite of x plus y plus z what the standard error estimate would be. So what is that? Wait, I screwed something up. 15.1, I don't know, why did I just get a completely different number? 64 equals square root times 15.95 equals, yeah, I did it twice. I got 5.134. 7 newtons. So sometimes it's an order of operations, like, because I started to go 15.95 times and then this, and I thought, no, I backed up and did 1 minus 0.8964, took the square root of that and multiplied that by 15.95. If you go the other way around, it may do something goofy like 15.95 times the square root of 1 minus, you know what I mean, depending on how you type it into the calculator. It may do some goofy stuff. All right, so it's okay. It happens. It's good to figure that out now. 5.134. So it means that, you know, this is roughly the standard error of the instrument. So basically, like, you know, the accuracy of when you add these three things up, PrePost scores, there's roughly 5.134 units of those scores that is due to error, fluctuation, on average. Okay. So how much reliability do we want? What's like the goal here? So typically we want values that are 0.80 or above. What if we don't have them? What if I don't have 0.80 or above? Well, we can take the Spearman-Brown formula from before and reconfigure it into what's called the prophecy formula. I always thought that was the coolest thing, the Spearman-Brown prophecy formula. Okay. The only thing is, what it prophesizes isn't super interesting. Like, it's not like it's prophesizing the end of the world. Anything else, it's just prophesizing what your reliability would be if you did if you added more people to it, or what the number of people you would need, or how many more times the number of items you have you need to get to reliability you want. So, not a super fascinating prophecy, but if you're trying to develop a scale, this can be very, very useful. So, what this does, okay, it says, again, it's just rearranging the Spearman-Brown formula to say, what is the number of times I need to multiply my scale to get the reliability I want? So here is the desired reliability, RD, minus 1 minus the observed reliability, and then the observed reliability times 1 minus your desired reliability on the bottom will give you the number of times you need to multiply your scale to get to that reliability. Okay, so let's say you have 30 items and this comes back as 2. You need to then go to 60 items. If you have 30 items and this comes back as 1.5, you need to go to 45 items, and that'll get you to the level of reliability you need, assuming that the items you add in are just as reliable as the ones that were already there. Okay, there's some assumptions there. So using the same continuous x, y, and z, I have 0.8964 as my reliability. Again, it has 3 items. If I want to get to a 0.95 reliability, I would plug that in as my R. My reliability desired is 0.95 times 1 minus 0.8964, which is my observed reliability. And then I would go my observed 0.8964 times 1 minus the 0.95, which is my desired reliability. If I do that, what do I get? I mean, I think I know what it should be, unless I'm incorrect in my thing here. Let's see if you worked it out. You get 2.2, I hope. RDRR. Anyway, sorry, that was bad. Oh, that actually was kind of funny. All right, RD, so the D stands for desired. I don't know why in the previous slide it flipped it. Like, see, RD, this R is supposed to be large like that. RD is the desired reliability, the reliability you want. And then RO, again, think of this is supposed to be big R. O is the observed reliability, meaning the reliability you have. So D is desired, O is observed. Yeah, it's weird. It's a font thing, I believe. It got this font switched. It makes it look like it's an I instead of a J. Yeah, it's supposed to be a J. So because 0.95 is my desired reliability, it goes there. 0.8964 is my observed, so it goes inside up on top. Then on the bottom it just reverses. The observed is here, desired is there. And what do you get? Anybody get 2.2? Oh, yay! All right, I like when I'm consistent with myself. Okay, so that means that I would need to be 2.2 times longer. So right now we're at 3 items. It's not very long. So 3 times 2.2 means I need to have 6.6 items, or roughly I would say 7 items. So if I go to 7 items instead of 3, I would then get to a reliability that's 0.95 or more. That's why it says nearly 7 items. I would just round up to 7. 7 items to get to the reliability that I want. Okay. Questions? Oh, sorry. Yeah, so I took the 2.2, which is the J that we got, and I said, all right, so I need a test that's 2.2 times the test I have. But the test I have only has 3 items. So 2.2 times 3 is 6.6. So I need to have 6.6 items. Well, I can't have a 0.6 item, so I just rounded to 7. So 2.2 times the original 1, 2, 3 items gives me 6.6, rounded up to 7, so I need nearly 7 items to achieve the 0.95 reliability. All right, the last part of this is something called attenuation. So, reliability relates directly to validity that we'll talk about shortly. Correlations are typically sought at the true score level, but the presence of measurement error can cloud, attenuate the size of the relationship. The more error in a scale, the more the reliability is attenuated. Okay, we can correct the size of the correlation for low reliability of the items. This is called the correction for attenuation. So what that means is if I want to take 2 items, right? So if I have X and I have Z and I want to correlate them. The correlation between X and Z. Well, if X has a reliability, let's see, the reliability of X is say 0.8 and the reliability of Z is 0.8. This correlation could never equal to 1. It's never going to be perfectly related. Right? There's noise here, there's noise there. Even if they're perfectly related, it's never going to come out to that because the correlation, the reliabilities are introducing error into each of the items. So I can't ever correlate X and Z together and get something close to 1. It's actually being, the correlation is being attenuated because of the reliability, the presence of measurement error. So I can correct for that. I can say, all right, I know that these aren't perfectly reliable. They're at 0.8. So I could compute the correlation between the 2 of them and correct for the fact that the reliabilities are not perfect. So this is this R with a hat on it is the attenuated, the corrected correlation. You take the correlation between the 2 of them, and you divide that by the square roots of the product of the two reliabilities. So this is the reliability of the first item, the first variable, reliability of the other scale test item, and you multiply them and take the square roots. This on the bottom is going to be your maximum correlation possible between the two of them. And I divide the actual correlation that I get between the two of them over that. Seeing as this is going to be less than 1, this is then going to correct for the fact that you're never going to get to a maximum of 1. It gives you a corrected correlation, or at least a correlation corrected for attenuation. Meaning that it's addressing the fact that the items are not, because one of the things that people never mention is that when you calculate an R, a correlation, or most anything, a T, anything, it's actually assumed that this thing is, that whatever you're correlating, that they were measured without error. That they're pure, untainted sort of variables, no error. So if you have error, because your reliability is not perfectly 1, then this isn't a true reflection of the relationship. So this is a way of sort of correcting for that. I think I have the... So for example, you have x and y are correlated at 0.45. X has a reliability of 0.8. Y has a reliability of 0.6. So the corrected correlation is going to be, so we have the new one, the actual correlation we have is 0.45. On the bottom we have the reliabilities, 0.8 times 0.6. That. So 0.8 times 0.6 times 0.6 equals 0.48. Now if I take the square root of that, I get 0.692, 693. It's 0.693. So this now represents the maximum possible correlation these two variables can have given those reliabilities. It's nowhere near 1. So let's look at what the correlation actually is relative to this. 0.45 relative to 0.693. I get it's actually closer to 0.649 as a correlation, which is a lot larger than 0.45. So 0.45 assumes there's no error. This is now addressing the fact that there is error and giving you an idea of how much they are related despite the error that is involved in their reliabilities. So the correction for attenuation. So the messier, sometimes the messier, less reliable items are, the more that's going to impact the correlation between that item and other items. So one way to sort of fix it, or at least address it, or try to get an idea of what it would look like if the items were measured without error, is to use this correction for attenuation, which can tell you a lot about the relationship between variables if that assumption had been met. I mean, if the no error assumption was actually met between the two items when you were correlating them. Questions about that? This is actually leading into the fact that reliability affects correlation. Right? The reliability affects its a variable's ability to relate to other variables, which means as we go into talking about validity, that's a whole can of worms, because it means if reliability is low, it affects a scale's ability to be valid at the same time. So validity depends on reliability, and so poor reliability can actually impact or make it impossible for a scale to be valid and measure things validly.